go ahead.
Okay, hi everyone. I'm going to be talking about volumetric rendering using Rust, specifically at reverse. So one slide about me. I'm Rosalie de Winther. Most people call me Rose. I enjoy skating, volume rendering, programming languages, which is why I'm here, and photography. I took this picture, which was nice, I think. So today, what are we going to do? First, we're going to have a look at what we want to get done, how it's currently being done in games, how can we improve whatever is currently being done in games. I'm going to talk about the VDB data structure. I'm going to show pictures from Breda, our in-house renderer, and I'm going to talk about some active research that I'm working on for my thesis. So first a question, volumetric, question mark. What's a volumetric? Well, things that have volume. Everything has volume, pretty much. So in graphics, traditionally, we have used meshes, and meshes are made up of triangles, and these define a surface. But we're interested in volumetrics, so things that don't have a rigidly defined surface. One of the examples is clouds. These can be rendered using triangles, or at least not like this. Another example is dust storms, smoke storms. Someone captured that video, I think in the United States. Looks cool. Would be cool to render that. More volumetrics. Explosions, these not only have smoke, but they also have light coming from inside because there's a fire or whatever. This, of course, adds a whole extra dimension because this is not just particles, this is also emissive particles. And how do we do this? How is this being done in games? So rendering a sky is pretty easy. You take 6 textures and you slap them around the player. If the player is not looking at an object, then we just render the sky, the cube map. So yeah, you can just put a bunch of clouds in your cube map and you will see clouds if you're looking up. However, this is static and quite boring and doesn't look that good. Can change based on weather conditions or something like that. So one of the improvements that people have done is they grab a texture and they slide it across the sky. Of course, it looks better, somewhat looks alive, but it's still a static texture which just slides. You could also do a bit more complicated deformations, like twirling it around to give an illusion of a storm, but it's, again, just a texture sliding on the sky. How do AAA games render a sky? Over here we see Red Dead Redemption 2. On the right we see Horizon Zero Dawn. Sky. These are two examples of very pretty sky, in my opinion. They use a method called analytical ray marching. You can see it on the top right. We see a camera. It shoots the orange or brown ray. This traverses a volume, and then at certain points in that volume you see the green dot. We check if that volume is hit by the sun. And we do this for a bunch of steps, and that's how we get our transparent clouds. So the way this is currently done in games is by using, they call it 2.5D, so it's not actual 3-dimensional data. They have a 2-dimensional texture of where the clouds are in the sky, and then the 0.5 dimension comes from noise textures. These noise textures make the cloud puffy and make it look 3-dimensional. And this is currently being used in AAA engines. So what about the fire? Because we also wanted fire. Below here we see Red Dead Redemption 2 again, still a fairly recent title. On the top right, we see Unreal Engine 4, one of the better looking engines, also quite recent. But there's definitely flaws with both of these techniques. You can, for example, see the fire. If you look very closely at the floor, you can see that there are clear slices of textures just being spawned. And it's just textures, nothing magical happening. And for example, this explosion of Red Dead Redemption 2, there's a bunch of fire coming out, but nothing in the area is being lit up, which is completely immersive. Well, if you point it out, it's completely immersion breaking. So this one cut it for us because we want to develop state-of-the-art rendering techniques which advance the rendering world. So how do we do this? How do we render things like this properly and physically correct? Well, we move to 3D data structures. So specifically voxels. I'm quite sure, well, I'm gonna ask, who knows what voxels are? Okay, that's good. So for those who don't know yet, a picture is made and is 2D, right? And now if we make that picture three-dimensional, we get volume pixels, we call them, aka voxels. So these, instead of defining squares, they define cubes. And every cube can have, for example, a density of particles or a density of cloud, whatever. But there's one critical drawback of using voxels, because in textures, the size of your texture, if you have a 1000 by 1000 pixel texture, you're using 1 megabyte of memory, roughly. But if you're using a 1000 by 1000 by 1000 three-dimensional texture, you're using 1 gigabyte, and that's not going to cut it for assets in a game. So, for example, on the right here, we see the Disney Cloud. This is a model made by Disney. You can download it online. And I did some quick math, and the half-resolution version of this Disney Cloud is 45 gigabytes and won't fit on your GPU, because GPUs have 24 gigabytes of memory at most. Like, the top of the line has that much. So this will never fit. So we're going to need some sparse data structure for this. So here we enter the world of VDB. This is a data structure developed, I'm quite sure, by Pixar or Disney. And has been a default in movie rendering for a while. So it's quite a lot more expensive than the techniques that I showed you with the textures and stuff. But for movie rendering, this is fine, because there they can have huge server farms with terabytes of RAM and render it that way. So what is a VDB? It's a sparse 3-layer B+ tree. Sparse meaning that the actual it's a tree structure where if the leaves do not contain any volume, those leaves are not stored. So if the volume is completely empty, we won't store any information pretty much, and it will be super small data structure. It uses 3 layers, as you can see here by the arrows. There are 3 indirections. There's the top level node, the middle level node, and then there's the leaf node, and the leaf node points into your actual voxel data. The voxel data is a density field of, for example, water particles of a cloud or smoke particles. And it's a B+ tree, meaning it's a binary plus tree. It's not a binary tree because it doesn't have 2 children. It's a binary plus tree because every layer has a set amount of children. And the way the structure works, as you can see down here, we can see 2 purple boxes. So these 2 purple boxes are the only things that are being stored in the data structure, because those are the only that store actual volume information. And then over here we see the same happening with the green boxes, because we don't have to store all the green boxes. We just store the ones which contain data. And the structure is quite simple, actually, because we just use every node only contains a bit mask and a pointer to the children until you are at the voxel level. So the bit mask tells you whether a volume is active or not. If there's a 0, that means there's no volume in that voxel. If there's a 1, it means you could traverse down the tree to find the volume that you are looking for. And this structure makes sampling your volume way faster, because if you know that a volume is, or a certain part of your volume is empty, so there's a 0 in your bit mask, you can just continue to the next thing you want to check. And these bit masks are, of course, very compressed, because they're single bits for large chunks of volume. So if you have one cache line of 128 bytes, then you have so many bits in there that you can traverse the entire thing in one cache line, and you're pretty much not even using L1 cache. So that's going to be way faster than just storing, for example, a 3D texture. And it, of course, has a massively smaller footprint, because empty space is not stored. So what do these structures look like in Rust? We have our node L1, that's the purple one. We have our node L2, that's the green one. We have the leaf, which is the blue one. These have child masks. and a child pointer. Everything is a U32, and we don't use actual pointers because all this stuff has to be sent to the GPU, and the GPU has to be able to use it. So these pointers are actually just pointers into a vector of the lower level nodes. So here we have our volume asset. So we have a name, we have some vectors of all the nodes. We need these vectors like this because our GPU, once again, requires everything to be in buffers. And this way we can easily transfer it to the GPU. And then there's some additional data for rendering. So the GPU version of this struct, we have a constants buffer. We have the L1, L2, L3, and the voxel data buffers. This is exactly what is on the GPU in our case. So if you want to use VDBs yourself, we created a crate. You can go look it up. It's this link. It supports parsing of Houdini Blender files and some other files, which you can find on the internet. Not everything is parsable. Sometimes they use niche flags or other things, but most of the files that we used can be parsed using this, and you get a nice volume data structure, which you can play with. Also, in that repository, you can find this program. It's using Bevy. It renders the VDB information, and you can fly through it. We use Bevy for rendering here, so all the voxels are triangulated, which makes it super expensive on the GPU, because every voxel gets, I don't know, like 36 triangles instead of one floating point value. So that's why it's quite choppy. And here we see, once again, the Disney cloud, the quarter res Disney cloud. So some debug information. Here we see the L2 nodes. So you can see a very core structure. And those are the active VDB or the active L2 nodes. In every one of these big chunks, you can see smaller cubes. Those actually correlate to the bits which are in the bit mask. So every little cube correlates to 1 bit. Here we look at the L3 nodes, same story, obviously a lot smaller. Once again, these again have all the bits and the pointer, and you can see roughly the Disney cloud shape again. Here we see the voxel data indices, so we can clearly see chunks. For example, the green part is one L2 node, the blue part is in one L2 node, the yellow part is in one L2 node, etc. So you can clearly see that not every voxel which is close in the world space is close in actual memory space because of this chunking system. Okay, now we will have a look at Breda. It's our in-house renderer, our beloved. And with many, many thanks to Emilio, he's sitting over there in the white shirt. He made many of the pretty things we can show now. I hope this plays at the correct resolution. Let me check. Sure. So here we see a smoke effect. You can shine the sun behind it. We can change the scattering coefficients, which means that depending on how far the particles fly through the densities, different colors of particles will get refracted differently. So that's one of our assets that we're using. Here you can see it again. Once again, in the less dense areas, you can see that red is being refracted more, and in the more dense, you can see that blue is refracted more. Here we see Disney Cloud half res. So instead of using 35 gigabytes, which wouldn't fit on a GPU, we can store it on the GPU. We can render it in our Breda framework. There is some noise. Their FPS is low. We're working on this. And again, this is a movie asset. This is being used by Disney. But this is in our game engine. So now I will talk about some active research that I'm working on. So firstly, compression. So let's have a look again at the VDB structure. I didn't talk too much about the actual voxel data, but the voxel data is stored in bricks. Bricks are 8 by 8 by 8 voxels, so that's 512 voxels. And if we want to compress this this actual bottom level data, because this is obviously by far the largest part of our data structure, because, for example, the L3 node, the blue ones, those store 1 bit for every voxel, and the voxels contain 4 bytes, a full floating point number. So if we can get those bricks or the voxels as small as possible, we will massively reduce our data structure size. One way to do this is to find similar bricks, and then if 2 bricks are similar, we can have the L3 nodes point towards the same data brick, and then we can reuse this huge floating point data. So how do we do this? Well, we could use a technique like k-means. Our 512 floating point values, which we use, can be the feature vector of our k-means. So then we get a matrix of n by 512. We run k-means on this. We find how many centroids we want, and then we can use those centroids as our new brick data. So this has a massive complexity if we actually use large volumes, because it has complexity 512 because our feature vectors are massive, times n, which is the number of bricks we currently use, and k, the number of clusters we want at the end. Of course, if we want 100,000 clusters at the end, and the number of clusters is obviously going to be higher than 100,000, then this is going to completely explode out of control. So we somehow have to optimize this method if we want to continue using k-means clustering. Another issue is the distance metrics. So normally with k-means, or one of the most common use cases is one-dimensional data, and specifically histograms, for example. And those can be very, very well described by using, or the distance between 2 histograms can be very easily described by using the Earth mover's distance, which sort of figures out it doesn't figure out gradients, but it's more of a fuzzy match than what we're doing now, which is just matching 512 values against 512 values. You have a question?
Yes, a clarifying question. Are you talking about lossy compression algorithms?
Yes, we are talking about lossy compression. Yeah, because it's pretty much impossible to find bricks which have the exact same floating point value. There have been papers about binary voxel compression, which aren't lossy and can compress very well, but we are specifically looking at floating point data. So for this compression, I tried to use an algebra, which was quite difficult. There's a bunch of generics and stuff, and I don't know, I wasn't very productive with it. And then I tried ND-array, which was a lot more NumPy-like, and I've been using NumPy for all my linear algebra for a long time, so I decided to stick with that. I can definitely recommend it for anyone who wants to do linear algebra. So now some of the results of this compression, the ground truth. This is a half-res Disney cloud, 650 megabytes, and we can see our index space over there again. So we can see there's clear chunks. Then we go to the compressed version. We use k as 1004. So there will be 1004 bricks, which will contain all the information for all for the entire data structure. This reduces the size to 87 megabytes, which is almost a 10 times decrease. And it took 12 minutes to compute this. If you look at the picture on the right, you can see that our index space is completely changed. But there's still some clear patterns, because at the bottom you can see there's mostly red. This is because the bottom part of the cloud roughly uses the same density information, and the top part has more like niche features which are more unique. So that's why there's a bunch of different colors at the top, and the bottom is mostly red and can reuse the same voxels. So here we ran it again, this time with K100. We got a 1 megabyte decrease in our data structure size, which is pretty good. I don't know if you noticed the loss in quality. I'm quite sure no one did. But these are different pictures. And using K100 resulted in 6 minutes of compute time. So this was twice as fast because the K was that much lower. Again, this has to do with the complexity of the k-means algorithm. And that worked really well. No one noticed the difference there. But that was a massive volume data set, of course, again, used in movie rendering. Now, if we try to use this technique on a smaller effect, like this fire smoke particle effect, you can clearly see that there is definitely a lot of, the quality is way worse. Their reduction is also only twice, uses twice as little data. So another part of my research is looking into animations. So I showed you a bunch of these like smoke effects and whirlwinds and explosions. So how can we make that? Well, last week I implemented this, and it's a very simple approach. It's a flipbook style. So we just have a bunch of VDB files, and every VDB file is one animation frame. And I tweeted about this. But now we can get smoke out of a chimney like this. You won't see this in any video game because video games currently don't use actual volumetric 3D volumetric data for their assets. So you will not see the sun moving behind the smoke and seeing these effects. So what's next? Animation compression. This is the final goal of my thesis. I'm going to combine the two. I'm going to run my compression scheme on animations to get a sort of delta compression over an entire animation sequence, so we can actually use these animations in our renderer without using gigabytes and gigabytes of data. So Emilio is going to be working on emission, I hope. And we will be able to get fires in our engine, and it's going to look great. Unlike the Red Dead Redemption 2 picture, where there was like a huge explosion and there was nothing lit up the road or the building, we will actually integrate this emission into our GI system. So if there is an explosion, the street will light up. Once again, this is, I think, barely done by any games if you actually pay attention to it. If it's ever used. And then performance. So the Disney Cloud was running at 6 frames per second, obviously not very usable, especially not in a game where you need 60. So we're going to try to improve the performance of our rendering algorithm. Thank you.
Okay, thanks a lot. Any questions?
Hi, thank you for the presentation. Well, have you ever tried, for the compression part, have you ever tried the hashtag?
Yeah, so the hashtag uses, doesn't use volumetric data structure, or doesn't use floating point data. So they use binary or integer data, and then you can use the hashtag. In my experience, they also created a lossy compression scheme where some of the binary data would get lost in favor of massive compression ratios, but that doesn't use floating point data. And we're specifically looking for these floating point animations of like density clouds.
So there are a lot of variation, well, apart from the hashtag.
Mm-hmm.
And this year in Eurographics, there's a new paper, employed based on the tag, not the hashtag,
Mm-hmm.
and it's from our group, so
Mm-hmm.
I would recommend you
Okay.
to implement this.
Sure. Okay. Yeah, maybe we can talk and you show me.
Yeah.
Okay.
And also it has the lossless and
Okay.
lossy compression. Yeah.
Anybody else?
Yeah, so I have a question. How do you pick this K variable? Do you have some kind of objective metric about quality of these things? Because this is just one example you have, you know.
No, I just completely ballparked it.
Okay.
Yeah, I was just mostly looking at, yeah, no, we don't have an official metric. I just look if it's good, if it's bad, can we use it? Especially in animations. Animations, of course, go way faster. You won't pay attention to every detail in an animation sequence. Then the quality maybe matters less. And again, it's still a game. Everything is ballparked. Yeah.
Yeah, so I was wondering, like, if you do this compression, then two adjacent voxels are less likely to be adjacent in memory, right? Does that matter, or does that magically not matter on a GPU? Perhaps, maybe I'm missing some detail there.
No, that definitely matters. So we store the bricks, right? 8 by 8 voxels, and those will be close together. So you will still have 512 floating point values, which are very close together. And of course, once you move to the next brick, then you're gonna have a gigantic cache miss, or could have a gigantic cache miss.
Okay.
But I am not sure about the performance impact of that specifically.
It would be hard to also take that into account in the compression to make sure that everything's well ordered.
Yeah,
I guess.
yeah, I would think so. That's gonna be hard.
Interesting.
Can you pass it on?
I would just like to add, if you need to sample something in the neighboring brick, then you probably also want to sample another thing in that brick. Then it's already in cache. So you just have that one big cache miss, and then you get very few cache misses again. So I do think the fact that these bricks are far away in memory is not as big as a deal as long as you have some spatial locality of your data out there.
Okay, any more questions? No, thanks. Okay, awesome. Those were some really pretty things.